Let us solve a problem using Gauss siedal iterative method. We have been given system of linear equations. We have the diagonal located coefficients are 20, 20, 20. We have absolute value of 20 is greater than or equal to absolute value of 1 plus absolute value of minus 2. Absolute value of 20 here is greater than absolute value of 3 plus absolute value of minus 1. Similarly, for the last equation, we have observed absolute value of 20 is greater than absolute value of 2 plus absolute value of minus 3. Thus, considering the three equations, we have verified that diagonal dominance property is satisfied. Now we will find out expressions of x, y and z from first, second and third equations respectively. We have x equals 17 minus y plus 2z divided by 20 from first equation. From the second equation we have y equals minus 18 minus 3x plus z divided by 20. From the third equation we have z equals 25 minus 2x plus 3y divided by 20. Now we will find out first approximation using Gauss siedal iterative method. We have formula for x1 given by x1 equals 17 minus y0 plus 2z0 divided by 20, where x0 and y0 are assumed as 0. Thus we have x1 equals 0.85. Whenever we are not specified with values of initial approximations, we will assume that x0, y0 and z0 are all equal to 0. Now our variable x has taken the updated value 0.85. This value will be considered while evaluating first approximation value for variable y1. Thus we have y1 equals minus 18 minus 3x1 plus z0 divided by 20, giving x1 equals 0.85 and z0 equals 0. In this equation we will get y1 equals minus 1.0275. Since now the variable y has been updated to the value minus 1.0275, for evaluating z1 we will make use of values of x1 and y1 which are available from the current iteration, which is the first iteration itself. We have formula for z1 given by z1 equals 25 minus 2x1 plus 3y1 divided by 20, where x1 equals 0.85 and y1 equals minus 1.0275. Giving these values in this formula, we will get z1 equals 1.0109. This is the major difference between Gauss-Jacobi iterative method and Gauss-Seidel iterative method. While Jacobi used all values of variables from the previous iteration, it was Seidel who suggested using the updated values of variables from the current iteration itself, and hence this method is comparatively faster compared to Jacobi iterative method. We have formula for second approximation given by x2 equals 1 by 20 times 17 minus y1 plus 2z1, where y1 equals minus 1.0275 and z1 equals 1.0109 from the previous iteration. Giving these values, we will get x2 equals 1.0025. We have y2 equals 1 by 20 minus 18 minus 3x2 plus z1, where x2 is the value of x which is taken from this current iteration itself, giving x2 equals 1.0025 and z1 equals 1.0109 from the previous iteration. We will get y2 equals minus 0.9998. We have z2 equals 1 by 20 times 25 minus 2x2 plus 3y2, where values of x and y are taken from this current iteration itself. We have x2 equals 1.0025 and y2 equals minus 0.9998 taken from this iteration itself. Giving these values, we will get z2 equals 0.9998. Similarly, we will find out values of x, y and z in the third approximation. We obtain x3 equals 1, y3 equals minus 1 and z3 equals 1. Notice that when you consider x2, y2, z2 and x3, y3, z3 values, difference between corresponding variables is very small, or these values are very close to each other, and hence we can terminate the iteration. Thus we have x equals 1, y equals minus 1 and z equals 1 will be the required approximate solution. If we had solved this question using Jacobi iterative method, since Jacobi iterative method is much slower, we would have performed till 5th or 6th iteration to arrive at this solution.